Good afternoon. Welcome to the Computational Science Colloquium series. Today we have the pleasure to welcome Professor Gustaaf Jacobs from Aerospace Engineering. We're gonna give a tour de force about particle-laden flows.
Thank you. Thank you. My pleasure to be here. I think last time I spoke was a while back, maybe 10 years or so. So it's good to be here again and to talk again. I'm going to talk about work I've been doing for quite some time. It's really been a career goal and a piece of career work that's ongoing. I use the word pursuit of high-fidelity simulation. That word doesn't come out of nowhere. We just said maybe it's there is a push or an urgency to it. It is a bit of a pun, actually. I used to tell a joke surrounding Will Smith and the Pursuit of Happiness, which is a movie, but that's a little bit dated, especially since he got slapped, or he slapped somebody else, but it ended up hurting him, I guess. And the movie about Pursuit of Happiness is basically coming from the Declaration of Independence, which I quote here, the first lines, which says that basically you have the liberty to pursue happiness. And the word pursuit is used very deliberately, as in you can never achieve it. And I guess we all know that, occasionally sometimes. But that's the same for my research goal. It is very lofty, but the process is more fun, actually, than the achieving of the goal. So I'll explain a little bit what went into it. These are the environments. Let me see if there it is. So these are environments where you might find particle-laden flows. This right here is a hypersonic vehicle. It's called the X-51. It flies at Mach 5 to 10, which is very high speed. Basically, you can go from San Diego to New York in about half an hour at this speed. And what's that? Yeah, you're happy? You want to try it? Yeah. So there is a combustor section in here, which is magnified. And effectively, the flow comes in at Mach 10 and is slowed down. And there's a combustor section here. And that's where you inject the fuel. This is basically a liquid. And that liquid atomizes, forms droplets. And the droplets interact with the high-speed gas. Now, that interaction right there is essential to the function of this apparatus. If you inject too much fuel, or if there's some sort of shock wave that occurs, the thing reduces efficiency or it might not work altogether. So us understanding this environment is actually really important. Now, this the scale of this is on the order of 10 to 30 meters. The scale of this is on the order of microns. The physics can be on the order of nano even. So we're dealing with a tremendous range. Now, other examples include explosions. Here in a mine, you may have dust that explodes. It's usually accidental. You have similar environments. The liquid in the air can condense at high altitudes. You get these sort of drops, and if you have a missile, these drops can impact on the missile and erode the missile, which is also not good for business on average. So the scales are very large. We have a range of perhaps 10 to the 12. Now, anybody knows that if you have that sort of range and you want to model everything, that you're in trouble, that we simply don't have the computational capacity to take care of this. So we have to model. We have to, I can do it here. Okay, there we go. So we have to model, and if we go to the very small scale, let's say one atomized droplet, then we could simulate the flow over each droplet. If we have a supersonic flow, you get this sort of shock wave pattern, and you get a little wake behind each particle. And just to simulate that, we need a grid of at least 100 by 100 by 100 grid points, a spherical particle. And if we only, let's say, simulate around 10,000 particles, we're already at the limits of current day computational power. Now, in reality, in one of these explosions, you're talking 10 to the 15 particles. So if you have a micron particle, a handful of sand, and you just throw that in the air, you're already looking at trillions of particles. So If you actually want to simulate the real scale, you need to simulate 1 trillion of these, not 1,000. And obviously, those two shall not meet, right? So what do? We model this first as a point, and we apply Newton's second law. We guess the forcing, or we empirically find the forcing, we apply it. Or we perhaps even consider groups of particles, like clouds of particles, and we trace the clouds. Maybe there is like 1 million particles in a cloud, and we trace those as a point. Now, in doing that, obviously, you're reducing the model, and with every model reduction, you lose fidelity. We can do each individual stage here. So perhaps the first thing that comes to mind is maybe we can marry these models. We can learn something here and propagate it into here and propagate it into here and then figure things out in a coupled loop, right? Now that has become somewhat of a thing that now that we have machine learning tools. Typically, I look at reduced settings to understand these physics, and this is an example of an experiment that's conducted at University of New Mexico. We had a joint National Science Foundation grant on it. You see here particles that are dropped from the top. This is actually sand, pretty much, the silicon particles. They're very fine. They're about a micron. And you see they're being dropped here. This right here is a shock tube. Basically, we create a shock somewhere over here, and it will wash through the tube. The way we do that is we basically pressurize over here. We break a membrane, and the shock will start moving. Now, the shock speed is typically on the order of 700 meters per second. That's maybe 1,500 miles per hour. And if we want to measure what happens, you'll see the shock come by. We obviously need very fast cameras and with very high resolution. Let's see. Watch carefully. There was, and there went. That's pretty much what we get to see. This is a slowed down image, a slowed down video. We have, I don't know how many thousands of images per second, but that's what we get to see. Just a few snapshots of that interaction. Now, obviously, there's no way that we're gonna learn what happened to all these particles when they started interacting with each other, right? For that, we need something else. We can simulate. This here is a simulation with one of those point models with a code of mine that I developed, and I'll talk about it a little bit later. But basically, we have a cloud here of particles. There's a shock moving through. There is a reflected shock. Basically, it starts moving the particles. The particles start dispersing. There's a wake. You see the shocks reflect. They go through the wake. They go through the particles. There's a ton of physics in this particular problem. Now, you could ask the question that I asked on the first slide. If you wanted to pursue a high-fidelity model that could simulate these types of environments, what type of problems do you encounter? That comes down to this combination slide that I put together at some point. So this is at least what I need to do. And it comes down to developing a predictive numerical method for the gas dynamic coupled with the particle dynamics. There's discontinuities in there. Approximation methods don't like discontinuities. You have singularities. Polynomials don't like singularities. You have a time-dependent problem. So there's no asymptotic mean. You can't do statistics on the mean. You have to do statistics as the flow evolves. Modeling means that you have a cloud of particles modeled by a single point. That means there is statistical moments on the subgrid scale you have to consider. So you have to do statistical modeling. The problem size is an issue. You still can end up with 1 billion degrees of freedom, which requires massively parallel computers, and both for the particles and the gas dynamics. And finally, perhaps, or most importantly, to trace each point, you need some equation that includes the forcing law, a forcing that depends on the gas dynamics and the dynamics of the particle itself. The V sub F is the gas dynamics, the fluid velocity. The V sub P is the particle velocity. These two together They determine the dynamics of this system, and that requires closure, and with closure comes uncertainty quantification that propagates through the system, which requires learning, etc., etc. Yet another field of mathematics and physics that needs to be treated or considered. Again, hence the pursuit part. There's no one that masters all these areas to the extent that probably is needed, right? So let's start. First thing, point particle model. I mentioned it. We basically consider a single particle with a flow around it. You can actually find an analytical solution for the force on this particle if the flow is entirely viscous. It's this expression right here, which depends on the difference in the velocities, the radius of the particle, viscosity, and density. Typically, we correct it empirically for conditions that are outside of this analytical scope, outside of this analytical set of assumptions. And you can, for example, correct for what is the Reynolds number. And this right here would be the analytical solution, the drag versus the Reynolds number. This right here is the analytical solution. Once the Reynolds number goes up, it starts deviating. These are experimental measurements of a single particle in a uniform flow. Of course, you could also have deviations because the particle is not exactly spherical. So you get a band, you get a confidence interval on this particular forcing law. So this forcing is typically somehow curve fit, and there is a confidence interval in the curve fit, right? Now that is pretty much a perfect fit for machine learning, right? You just start feeding data into a surrogate, into some sort of response surface, and you get to quantified uncertainty. We started doing this in, we as a collaborator of mine at University of Iowa, we started doing this using mesoscale simulations, these small single particle simulations. We started extracting the forcing laws in a wide dimensional space. This is the number density, this is the Mach number, and other parameters. Yeah.
But also there are direct numerical simulations.
These are exact Navier-Stokes solutions, yes. So this right here, we started doing this in 2010. If you have a historical understanding, then not everybody was using neural networks in 2010. So we were some of the very first to do it. And we also spent a lot of time on surrogate models. So we developed several Gaussian methods with confidence intervals using Bayesian estimates to get to the confidence interval. You feed this into the reduced model, which is here. These are the Navier-Stokes equations. And these are the particle equations. You get the kinematic equation for the position and the dynamic equation for the velocity. And the forcing law here is central to this dynamics being correct. Yeah.
And just to clarify, is that picture an array of particles for which you're doing the exact?
Correct. I can show you. I can show you right here. Here's
You're using those results to feed into a neural network model that will then allow you to do larger sums.
Absolutely, yes. Which is very challenging. These are some of these simulations. So we have simulations of a shock going through a limited set of particles with, this is a 1% by volume occupation of the particles. This is 20%, different Mach numbers, 3.5, 1.5. And what you see is that these clouds, that they absorb the shock, they dissipate the shock. We call it mitigation. In fact, sometimes you just put spray of particles into a shock just to make sure it weakens. For example, you have an explosive coming towards you, you can just release a whole bunch of spray and it would reduce the strength of the shock. Yes? So how do we learn the forcing from this set here? That's it's another question. It's not just let's plug it into a surrogate. We have a limited sample set, but it's not homogeneous, right? It's not easy to infer or apply a machine learning model. Now, before I go there, this right here is a reduced model. The forcing is central. It forces the particle motion, but it also forces back the momentum law of the gas. So this is a feedback mechanism. And effectively, you distribute each point, a singular point, according to a Dirac delta, to the X space, the uniform space, the continuous space where the gas equations are defined. I'll come back to this later, but you can imagine that that doesn't lend itself to polynomial approximations very easily. Okay, so here is a set of particles. Particles are numbered. Here are some of the forcing histories on each particle. You see the force goes up a little bit and then it sort of settles down, which is typical. If the shock goes right by the particle, the pressure changes very high and you get a sort of settling. Now you also see that none of these forces are exactly the same, right?
It's chaotic behavior.
It's rather chaotic. If you look at this set here, you see shocks are scattered all over the place, ping-ponging around, wakes are interacting. So this is not a very clean mathematical problem, right? So what do you take for the average? What do you take for this volume? We've played around with that, tried to figure out what is a good homogenization. And we use an average. This is one of the models that we converge to. It's basically the essence of our neural net. It's a Kriging model, so it's based on Gaussian fitting. And we typically have a mean, and then we fit statistically the expectations according to the Gaussians. But we change those kernels quite a bit. We have something called adaptive dynamic Kriging. And the adaptivity ensures that these models are convergent. So the more points we use, we actually monotonically converge to some surface. With a Bayesian prior, we can also get a confidence interval. So if we have, let's say, 11 mesoscales, this is our forcing law with the confidence interval. We increase to 40 based on this information. We can improve the fit and reduce the confidence interval. Now, again, we were doing this in 2010, not in 2025, right? That kind of works, actually. So we use this forcing law. We plug it into a point particle model, and we get solutions that are actually similar to the direct simulation. So we compared a point simulation to a direct simulation and implemented our forcing law. So we basically query the response surface, if you will, depending on the flow conditions. We also gave up on it at this point. And the reason we gave up is because we have a hard time homogenizing, understanding what we should take as averages. Bigger problem is that each simulation, each one of these, costs 3 weeks on 500 processor. So we have, for each data point in our surrogate, we need to take 3 weeks on 500 processors. And at some point, the program manager that funded this work asked, so how much time does it take? So this much. He's like, oh, wow. And that was pretty much the end of us looking at this any further. Luckily, there was an alternate way, and Uday and I, we split ways. He was the guy that did the high-resolution simulations, and started looking at this problem differently. Again, think of pursuit. There is another way. And basically, we started framing this problem in the context that centers around forcing. So this is a forcing law, this F of A. A is the difference between the dynamics of the fluid and the dynamics of the particle. And we said that this F of A is basically random. So we have random coefficients scaled with some basis function, some function that we like. This could also be the summation of random coefficients with different basis function, like Chebyshev models. You get polynomial chaos. If you look at it this way, basically what we've done, we got Newton's second law here, but it's framed in the context of the two players in this particular system, U and UP. And these are not cooperating. They're not friends. One is resisting the other. And in many ways, that puts it in the realm of game theory. And in a way, what we have here is a somewhat classic statistical mechanics problem that combines and has the potential of making Newton, which is this guy, shake hands with John Nash, which is this guy. This was generated with AI, by the way, this picture. Yeah. Now that might apply this particular setting to quite a few problems. For example, you could have swarming of sparrows. They are clearly interacting based on a continuum with something else. There's an observational particle system. This is predator-prey. We have one player, the predator. We have another player, the prey. And they are fighting with each other. This right here is the spread of COVID over the planet. And there is something similar. There's transport of humans, and there is the general infection rate of COVID, right? So this sort of generalizes, if you will, as classical mechanics does. And if you look at the statistical classical mechanics, you look at the derivations of the relevant equations, typically you end up with some sort of Fokker-Planck equation for the distribution, probability distribution of a species or a particle species. Our model can be subjected to that as well. Here's the generalized model, and recognize all I've done is taken the summation of random coefficients with basis functions here. Once we take this, we pose this, we have actually removed from what is typical stochasticity. So if you look at Brownian motion, typically the paths of each particle are according to a random walk or a Wiener increment. And based on that, you can derive a Fokker-Planck equation, which is a convection diffusion equation. You can apply to this also similar, let's say, theorems. We apply the Liouville theorem and derive a Liouville equation, which basically takes this Lagrangian equation, which is random. The x and u are also random, right? They're not deterministic solutions. You get f, the probability density function of the coordinate x, u, and the coefficients z and psi in this equation. And this governs the behavior. Now, what you see is that on the right-hand side, there is no diffusion term. There's no Fokker-Planck term, if you will. That is, in fact, replaced by a diffusion velocity. So you see these coefficients appear as velocities in the convection term. And it actually allows us to model diffusion. This right here can be modeled deterministically with this equation. So we no longer actually have to do the random walk. We can deterministically solve a diffusion problem without having a diffusion term. And again, this is generally applicable. What's nice about these coefficients, unlike Wiener increments or random walk, this doesn't have to be Gaussian. So we can take these coefficients to be any distribution we want. And yeah, of course, having a hyperbolic equation, which is what this is much easier to solve than a diffusion problem. Okay, so how do we find forcing? Right, that's what this was about. Not necessarily about posing new forward models, which is kind of nice, but we start with basically the dynamic system again, with a forcing that is, in this case, deterministic. We have a velocity field here. It's ABC flow. It's basically a vector field that varies according to sines and cosines. And there is a particle trace here, this blue line, which is basically the manifold that results if you trace this inside of this velocity field. Now you see here the magenta line is basically the force vector that changes the manifold. And this force varies according to the relative difference between the velocity of the gas and the particle. You see it varies over the path. Now we say, what if we don't know the path? We only have snapshots. Let's say if the shock particle problem, we only have a first and a last snapshot. Could we infer or determine the forcing? So what if we only had the beginning and the end location and we didn't know the forcing? Could we recover that forcing, right? Well, that puts us in a somewhat of an optimization problem. We say the forcing is basically represented by the summation of coefficients with modes, polynomial. We actually take a Fourier series here. And we say the cost function, what we want to achieve and optimize, minimize, is some measured location to some forward location that is predicted based on a guess of the forcing. So we're guessing a forcing, we're predicting something, we want to minimize this with this constraint right here. Now that puts us in the realm of inverse modeling. Basically, you can use a Lagrange multiplier to constrain the forward equations with the cost function. And then the cost function, which is a function of the unknown coefficients of the polynomial, needs to be optimized in terms of the coefficient. So basically, you need to find the coefficients to satisfy this right here. This is work that's done together with Professor Wang in my department. Zijan, who's here, is a student that's working on this as well. We have extended this a little bit, and maybe someday he can talk about that. But in order to be able to optimize this, we need to know what happens to this x dagger and u dagger. And we call this the adjoint equations. They're basically the Lagrange multipliers. We need to know what they are if we change the distance of the particle location just a little bit. So if we have a deviation of the path, then we need to understand what happens to the deviation of the forcing and the deviation of the coefficients. And that x dagger and u dagger play a major role in it. So basically we start deviating, and the path that's really close by that deviates, we might not know. We might not know the fluid velocity there. But we can if we Taylor expand it based on information we have on the current path, right? So if we know the gradient and the velocity on the current path, we can find the velocity at the adjoint path. Also brings in a little bit of a limitation, but more about that later perhaps. But the bottom line is that we can actually show that these have to be zero. We're not really interested in the deviation of the path. We're interested in the deviation of the coefficients. So if we say these are zero, then we have an equation for how this alpha change responds to the change in the cost function right here. So we have a gradient optimizer, if you will. So that leads to this right here. We have the forward equation, we have the adjoint equation. It's actually solved in backward time. So we have an adjoint trace to this forward trace. And together they form solutions that we can plug into the gradient optimizer of the cost function right here. So we basically update the alpha coefficients according to this gradient right here. Here is an example of how that works. We have a band that initializes the forcing. This is our guess. This is what we know we're supposed to get. Yes? So that's our, yeah.
So this works for continuous flow fields, but you're interested in discontinuous flow fields?
Yes, yes, also coming up.
Okay.
Yeah, lots to do. Probably not going to solve it all. Yeah. But here's the forcing guess. This is what we are expecting to guess. This is a fabricated problem with a known solution, right? But we pretend we don't know this, right? This is what you get if you gradient optimize the solution. And what you see is the cost function has gone down with iterations, as it should. And this is the resulting forcing function for each individual guess. So the red one is a different guess, and you get a different final forcing law. Not very good necessarily. It's better in a certain region than in another region. That is clear also. Now, what has happened is that the path between these two has experienced this particular relative condition a lot more in this region than over here. Maybe it just saw this relative velocity once, but it saw this relative velocity a lot more. We are converging to something that looks like the forcing. We can actually make that a lot better if we have our cost function include more measured locations. So if we have more snapshots, we can actually do really well in the region where we get lots of occurrences of our conditions. This converges as well. So at least to a engineering accuracy, we're still working on converging this formally according to the polynomial that is still up in the air, but has a lot to do with the number of realizations we have at each point. So the more realizations you have, the lower the error typically gets. Okay, changing gears a little bit to that singularity, at least one of them. It's if we have the forcing, then we have to distribute this forcing over a continuous space. And it is a singular point, so the distribution is according to a Dirac delta function, which is, again, not an easy function to approximate. If you were to approximate it, your first choice and guess would probably be a Gaussian or something like that, a Dirichlet kernel, something that looks like a Dirac delta according to the definition of a Dirac delta. If you have a low order method, you probably use a 10 spline or a very simple spline, a 0th order spline. Now, the method that I tend to use for simulation of gas dynamics is the discontinuous spectral element method. I worked with David Caprivo when I was a PhD student. He's an adjunct. He's one of the creators, I would say, of this method in general. And what you do is if you have a domain like an airfoil here, you map the element into non-overlapping elements. And on each element, you project a high-order orthogonal basis. With mapping and metric terms, you can basically do all operations on this element right here. And if you use a Galerkin approximation, you can minimize the solution to the gas dynamics, the governing equations of the gas dynamics. So it's a really nice method. It has a lot of good properties. I won't go over it really, just to tell you that we have a code that can do a lot of things. So it can simulate flow over airfoils, LES. It can capture shocks. So we have a shock capturing capability. We simulate flows in ramjets. We simulate shocked problems and shock diffraction problems. We have a particle tracer. It's parallel. So the particles collect back with the gas. So we have a two-way coupled set of particles. It's parallel. We also have a chemically reacting model that just came online. Just about half a year ago, we have the ability to simulate chemically reacting flows. We have a cloud model, and I'll talk about that in a second, but basically we could simulate point clouds and distribute them according to these sort of wider distribution functions, Gaussian distribution functions. This here is perhaps the last thing I'll show. These are so-called Lyapunov exponent visualizations. You basically look at neighboring particles and determine their divergence over a finite time. And you can plot the separatrices in chaotic flows. So you can sort of understand the coherence based on separatrices in a fluid flow field. Back to the two-way coupling, back to having a particle and needing to distribute that to neighboring points. In the two-way coupled algorithm where we solve the gas dynamics, in our case with the discontinuous Galerkin method, and we track the particle in its Lagrangian frame with its dynamic equations, we use a Runge-Kutta method for that. We need to interpolate to the particle, so the gas dynamics is interpolated to the particle, and we need to distribute this particle influence over its neighboring grid points. And again, that is a Dirac delta. Intuitively, you might use cardinal B-splines. You might say if we have a high-order B-spline, we get consistent high-order convergence. That would be very intuitive and natural to do, right? Yeah.
And the TBDs were you use for capturing the shock?
It's actually for integration of the particles. If we have a particle near a shock, we need to bias the stencil. We do that using ENO. So we find the divided differences, and there's a sort of a wavelet analysis that biases the stencil. And then we don't have to interpolate over the shock, right? This for distribution is actually not so important. The distribution is kind of diffusive. So it diffuses the solution a little bit as well, which is pretty much what you want to do. The TVD is for the particle tracers. It's just a little extra robustness, if you will. Okay, so these cardinal B-splines or Gaussians, Gaussian-like, are basically summed with a way to get the total forcing of a cumulative set of particles. So we have many, many particles, each has a Dirac delta distribution. It's effectively a summed approximation of some radial function that gets you a source function.
The previous one, please.
Yeah.
Just to highlight that Suarez was a PhD student in our program.
Yeah. Actually, some of the work I'm going to discuss now was done by Giampiero here. And he's done an amazing job. He was a pure mathematician, really, a background from Venezuela. And Jose was kind enough to send him my way when I was just starting here. And he did a really good job. He actually ended up being a professor in Venezuela, but then the Venezuelan economy didn't do so well. And he's moved around a little bit. He was a professor in Colombia for a while as well. But in any case, we simplify this analysis to this advection equation, and the source is a Dirac delta that is distributed at the zero location plus a time, so it's time dependent. Now, if you solve this left-hand side with a spectral method, the type of higher method I'm using, and you're approximating the Dirac delta with a Gaussian, then this is the solution you get. We initialize with a sign, so the sign is sort of advected. And wherever you have the singular source, you get the jump condition in the solution. If you approximate this Dirac delta with a Gaussian, you actually get a solution that dissipates the global solution entirely. And there's actually very little you can do about it. You never actually match or converge to this particular solution. Perhaps in the limit that sigma goes to zero, which is when the Dirichlet kernel basically becomes a Dirac delta. But the convergence behavior is very slow and very diffuse. Okay, so we need to sort of look at Dirac deltas, and that's exactly what Giampiero did. He looked at delta sequences, which have basically got the compact support epsilon and are generated by a generating function f, which basically scales with epsilon and x over epsilon. And it should have this property right here, which is basically if you convolve a Dirac delta with a solution, you should better get its solution value back, right? So these are basic properties of distribution functions. It also places the analysis in the realm of distribution functions. And that was something Giampiero was particularly good at. He basically used this, you could say theorem or lemma, whatever. But basically, if you have the moments of this generating function, if they are zero, then you can show that the delta sequence converges according to the number of zero moments. M is the number of zero moments. So if you have zero moments, then delta epsilon tends to the delta according to the compact support epsilon to the power m plus 1, right? That's faster than a Gaussian because a Gaussian doesn't have any zero moments. The Gaussian only has, it already has the first moment, right? It has variance, second moment. So this is the reason the Gaussian doesn't converge to the Dirac delta solution. Now all you have to do is basically create such a delta sequence, an approximation, for which the projection Q onto some polynomial space, so Q projects this onto a polynomial space, is bounded by that moment error. Now, if it is, in that case, the projection can be of the same order epsilon m plus 1. So if you bound the solution error with this moment error, then you're in good shape. You get high order convergence. That occurs when epsilon is of this order. So when this error matches that error, you can show that the epsilon is around this. It's an estimate. You could put that the other way around. You have to take epsilon a certain way to get a certain convergence. And this is what such a function looks like. You can actually generate them. We have. You use basically a Gram-Schmidt type of orthogonalization to satisfy the properties and its constraints of this polynomial. And you get a function that they're called Mexican head functions, actually, because they look like Mexican heads. And there's a little bit of a negative part to it, and that negative part ensures that the moments are zero. So if you integrate this, take the variance, you get zero. And that works beautifully. If you have a discontinuity and now you use a Dirac delta, it's still a regularization. So exactly where you have the discontinuity, you are going to get a zero order error. But away from it, you get formal convergence. So this thing, which is unsteady, I'll show you, the shock moves unsteady through this medium, right? But away from it, we have formal convergence. So away from it, the error goes down according to the number of moments or the smoothness, whatever we decide should dominate the convergence rate. Okay, so one might, this actually works for the summation of Dirac deltas too. This was harder actually. We had a cloud of particles modeled by the summation of two Heaviside functions. So you sort of get a step function. And you can approximate this with the summation of Dirac deltas. You have to do a little bit more work. But in effect, it comes down to the same properties and the convolution of Dirac delta with an underlying solution. And you can show that you can get formal convergence inside of the cloud. So not just away from it, but also inside. And the interface here is still zeroth order, but again, what's inside is this. If you use a Gaussian, that's what you get, which is absolutely terrible. So if you were to use, let's say, simulate plasmas with particles, charged particles, Maxwell's equations, you couple those, you use Gaussians and particle and cell approaches, this is your solution. It's really bad. Okay, so, you think that's good. We've done a lot of work here, right? We got the coupling, we got the forcing, things are converging. What is next? Well, we're still not at a process scale. We need to be thinking of clouds if we want to go to a process scale, right? Okay, so that's next on the agenda. The nice thing about clouds is that they're not singular. So if we consider those to be singular, we don't have to distribute according to a Dirac delta, perhaps, right? Okay, so we started looking at the same equations, the dynamic equation, and he said, what if we have a group and we statistically average the group to a point? So we basically take the ensemble average of the velocity difference here. Then there's a few things, such as the forcing term, that we don't know, that we maybe want to infer at the point, right? Now, the way we consider that is by Taylor expanding the forcing around the mean or the center of the cloud. Now, if we do this averaging, we get these terms right here. We get higher moments, and we have a closure problem, classic closure problem. So we need high order equations, and we can find those. These are the high order equations, and technically there's high order moments to those as well, but we eliminate those. We say they're zeros. So we model let's say the influences of the averages and the variances on the system, and we use Taylor expansions to account for the correlations between the forcing and the distribution of the velocity in the sample. That can be closed entirely. This is what that looks like. This is a stagnation flow. It's basically a hyperbolic system to a singularity. And this guy right here is an animation of the cloud model. You see 40,000 Monte Carlo particles, and you see this green cloud. That's a one cloud point simulation. So instead of simulating 40,000 particles, we're simulating only one point according to this moment model. We track the moments. And these are the comparisons of the variances of the locations and the velocity. So the comparison is good. You may say a simple example, do a more complicated example. This is a box turbulence. So this right here is the computational model. It's a box. That's a set of particles in the center. And we release them in the center. And you see, you basically get the dispersion as if this were a cup of tea and you were stirring it. You would see that one drop becomes this sort of really intricate manifold. And we release a whole bunch of particles in it. And then you see these sort of jelly beans. They model a system of particles. These jelly beans are basically prolate spheroids, and their principal axes are determined according to the moment model. And that matches as well. Okay, last thing I'll discuss, because I think I'm kind of running out of time, and I want to leave a little bit of time for questions as well. We can use this to infer the forcing also. So we can say, what if we had a forward system, like so? And we rewrite this a little bit. We say if Q is the solution vector, it's X and U, and R is the residual. So it's the right-hand side of these equations. Then we can apply the method of averaging. We split this instantaneous solution into its mean and its fluctuation. We can apply the averaging, neglect high-order terms, and this becomes our forward equation. This becomes the equation for the second moment right here. And we can do the same things that we did for the deterministic particle. We can find the adjoint that minimizes a cause function right here. Now, we have a moment model, so we would typically minimize both the mean location and the variance. So if we had a sample set, we had a cloud, it would be at the beginning, it would be at the end. We would determine its mean and its moments, and then determine the mean forcing and the variation of the forcing, the variance of the forcing. Here's an example. We considered it's basically a cylinder flow, and we have a group of particles here. These contours are of the vorticity field, so these are coherent vortex structures in the gas. And these particles, they're sort of advected and give you this final set of particles here. Let's say we only knew the beginning and the end of this right here. Can we determine the forcing of the sample? So that's what that looks like. Pretty chaotic, pretty complex problem here, right? It's still simple for engineers, but this is has a lot of content in it. What if we had different guesses for the forcing? We didn't color them here, but we have different bands. Then we would get different solutions, right? Different dispersions of this group of particles. This is a probability that we hit a certain velocity condition. You see, it's much more likely we hit the lower velocities than the higher velocities. Keep that in mind. This, again, we assume the forcing to be a polynomial, and let's see if we can learn the coefficients. There's something that happens if you were to use a single particle problem. You might not know which initial particle belongs to which end particle. So if we go back here, let's say we might not know if this particle matched one of these, any one of these, we wouldn't know that. If we took a snapshot of our shock particle problem, we wouldn't know which one belonged to which one. So if we just randomly picked one of these, the forcing inference would actually be really bad. We wouldn't get anywhere near the forcing model. If we would pick the right one, and we would pick all of them, and we would use a deterministic procedure, we get pretty close. If we pick the sparse model, which accounts for the mean and the variance, we only need 1 point. Two statistical measures, the mean and the average, the mean and the variance. And we actually infer the forcing for the group, like so. Okay, this works in a two-way coupled setting as well. I will skip that. I think it's Friday afternoon. It's good to stop. But you see, we can actually model groups in a shock environment as well. We don't need to use Dirac deltas. We can use Gaussians, and that converges as it should. And to finish off, I'll reiterate: this is just a pursuit I've been doing this for a good 25 years, and I suspect I can do it probably another 25. I'm not sure I'm going to be doing it for that long, actually, but we'll see. So it's a rich area, and there's lots to understand. We've made significant contributions, and I think it's an area also that lends itself to generalizations that sort of find applications in other places. So that's kind of fun as well. So thanks for listening, and I'll take questions.
So you just said it's a rich area of study. What use cases in the real world do you think you can apply this to?
Well, to any of the problems where I showed you in the second slide, basically, right? So the code at this point is set up to run really large-scale problems. So we apply our code to the simulations of what's called an aerospike nozzle in my group. So these are basically the momentum delivery systems on rockets. This is funded by the Air Force. We're looking at retrofitting of gas turbine engines with hydrogen fuel. So they're typically using hydrocarbons, but hydrogen is creating a friendlier, environmentally friendly product. It's water. Hydrogen and oxygen become water. So we apply these types of models and methods to that, but it could be, there's legion problems. It could be rainfall or caustic formations of water. It could be plasmas, as Satish's here. I have plasma codes could be applied to that. And we're actually working on the predator-prey model as well. Yeah.
Are you getting a patent for any of this?
No, not really. No, not.
Let's see, we have
sorry.
before we go to pursue happiness, let's see if there is any. Not, let's thank Gus one more time.